just recall everything, whatever, however basic it might be. So a field is a set with two operations. So just to distinguish from usual addition, I'm just writing it like this. So it's a set with two binary operations, and if with the plus, of course, we won't be writing like this. We would put just addition. So this is a commutative. So this is the abelian group. And with uh, additive identity, usually written as 0. And when you take the set of all other elements except this 0, then that set under the second operation is another abelian group. And of course, these two operations are related by distributive laws. So distributive laws hold. So there would be only one distributive law because of the commutativity. And by finite field, we would mean a field which has these properties where the set F is finite. So we start with examples. So let me just start with some examples. So the first example is for a prime P, the set of congruence classes modulo P. So for a prime P, so ZP, okay, let's write it here. So ZP, the set of mod P is a field with usual addition and multiplication as defined for congruence classes. Is a field. So that's easy to check. So the second example. So the first example tells us that given any prime number, we have a field of that order. So we have fields of whose order is prime. So given a prime, you have a field whose order is prime. So the natural question is, does there exist fields whose order is not prime? The answer is yes. And the following example gives you such a field. So that's also an small exercise. So let I define something. So let F be a field. F be a field. And we define this set S2 of S2 of F to be matrices, 2 by 2 matrices with entries from F. So matrices are of this form, X, Y, and minus Y, X. So these are generally called skew symmetric matrices. Belong to F. Of course, you can do it for an infinite field F as well. our consideration would be for finite field F. So consider this set, and then it's not difficult to show that. Uh, so just so that can be an exercise. It's easy. That is 2 of Z3 is a field. Is a field, but S2 of Z5 is not a field. So this set is going to form a ring. So the only problem would be in inverting. So the only thing is to check that every non-zero element has inverse, and that would be possible if you are taking these matrices over Z3, and won't be possible if you are looking over Z5. So that's the thing to be checked. And so then if you consider this Z3, then and these 2 by 2 matrices, so it's the just the number of pairs x and y, x belonging to Z3. So you have 3 to the square elements, so you get a field with 9 elements. So S2 of Z3 is a field, once you prove that it's a field, is a field of 9 elements. So therefore, there are fields whose order is not prime. We would so the first thing that we are interested in is to classify the order of finite fields. So we would like to know what order a finite field might have. So we have already examples that for all prime numbers p, there is a field of order p, and also there are fields whose order is not prime. So we'll just figure out what the rest are. So all of them. So that's an example. One more example. So one more example which would be motivating for later work. So one more example that also I'm putting as an exercise. So consider, again we are constructing a field of 9 elements. So consider Z3 x. So we're looking at the polynomial ring with polynomial ring over Z3. So these are the collection of all polynomials with coefficients coming from Z3. So that forms a ring. And we look at the following subset of this. We are calling it F9. It's going to be a field with 9 elements. That is to be checked, but I've just list the elements. So I'm just writing it by listing all the elements. So it contains 0, 1, and 2. So the constants coming from Z3, and some polynomials, which includes x plus 1, x plus 2, 2x, 2x plus 1, yes, so 2x plus 1, and 2x plus 2. So these are all the elements I'm collecting in F9. So that's just a set. We need to define addition and multiplication on this. So addition is just directly addition of polynomials. Multiplication we would define. So let me write this. So let ax and bx. Okay, ax and bx be two elements from this set F9. Then the multiplication is defined as follows. So you multiply them as polynomials. So just use polynomial multiplication and then read it modulo x square plus 1. So the multiplication. So two binary operations. First is addition. Addition is just simply addition of these polynomials. So whatever you get when you add those polynomials, that's the addition. And multiplication is the following, that just multiply them and then read modulo x square plus 1. So, so this modular arithmetic with respect to polynomial is just same as modular arithmetic with respect to integers. Just to look at an example, let's take two polynomials and multiply. So suppose I multiply x plus 2 into say 2x plus 1. Then I'm just so multiplying as polynomials. So 2x square, and then the x term would be 4 plus 1, 5, and constant is 2. So this is 2x square plus 2, and then you have 5 of x. So 5, of course, you have to read modulo 3. So all constants are coming from Z3. So this is read modulo 3. And okay, sorry, this is 1. I've taken 2 common. So this is 1. So x square plus 1. X square, so we are reading modulo x square plus 1. So this would just be 0. And this is, so 5 is 2 modulo 3. So this is just 2x, which is in the set. So that's how we multiply. So we read mod x square plus 1. So essentially we are dividing by x square plus 1 and take the remainder. That's what the modular arithmetic will do. And so it is here. And with this addition and multiplication, F9 is a field of 9 elements. So we have examples of fields of order, prime order, and also element of order which are not prime. So there were interesting exercises in regarding these fields, so which I would post separately. So I'll just email some set of problems that you can think about. So the next thing what we do is define characteristic of a finite field. Characteristic of a finite field. Let me explain. So if plus and dot, so we would just go for the usual notations, just multiplication, and either we write a dot or just use common, use the common notations, but of course with this in mind that these are just notations. So let 1 be the additive unit, oh sorry, multiplicative unit, identity, with the multiplicative identity. So I multiplicative identity. So by that I mean that it is so 0 is the additive identity, and this is the identity element of the group, of this group. So so 1 is the identity element of if minus 0. So if without the 0 element, which is the additive identity, and so this forms a group, and the identity element of that group is written as 1. It has nothing to do with 1, just write it as 1. Yeah. So for any positive integer m, I would just write greater than equal to 1, just to make sure that we are not looking at 0. So for any integer, I can write m1 to denote sum of these ones So just remember that this is the integer one, and this one is not integer one. This one is coming from the finite field. This is the identity. So we use the same notation to make things easier. Uh, Otherwise, it will be notationally cumbersome. But this is something to be remembered. So M1 simply denotes the sum of this multiplicative identity M times. So we just add them M times. So although it's in the multiplicative group, but this is a finite field. This field has an additive structure, so the addition makes sense. And yes, so and if you look at all these, so M1 with M greater than equal to 0. Okay, so we also define 0 of 1 to be 0, the additive identity. This 0 is integer, this 0 is the additive identity. So if you consider all of this, uh, yeah. Yeah, in fact more. So you can define for any z. So if m is negative, so if m is minus n with n greater than equal to say 1, then m of 1 is m of 1 is mm, minus of n of 1. So n of 1, n is positive, so n is just sum of 1 n times, and then you can consider the negative of that. Yeah, I mean, so either way you can consider. You can just consider the negative of this element, or you define it like this. So this is all the same. Uh, so this all these multiples, so m1, so this forms a subgroup. So forms a additive subgroup of f plus and therefore the order of one, so additive order of one, so order of one, that is so just denoted by O1, divides F, the order of the field, order of the group, order of the additive group. So order of this element divides order of the group. So order of every element divides order of the group. So that is this divides this. And this order is called the characteristic of the field. So we define O1 to be characteristic of the field. So the first observation is that the characteristic has to be a prime number. So let's write it as a lemma. So there is another equivalent definition. So characteristic is also the smallest integer m. So because just coming from order, so characteristic because it's the order of one. So characteristic is the smallest integer, smallest positive integer m such that m of 1, so 1 added m times is 0. That's just from the definition of order. Order is the smallest value of this. So that's important. And then lemma. So the first thing we notice is that characteristic of a finite field has to be a prime. Finite field is a prime. Let's see why is that. So proof, suppose not. Suppose m is the characteristic so I would just write chart. So characteristic of f, let's write finite field f, and m is composite. So suppose, if possible, suppose characteristic is composite and m is composite number. So m is composite, so m can be written as m1, m2, where m1 and m2 both are, so it's a non-trivial decomposition. So this is greater than 1, m2 is also greater than 1. So composite number will have a decomposition like this. And so m of 1, so 1 added m times, so that's a sum of 1 added m times, and that can also be written as m1 of 1 multiplied by m2 of 1. So that's just a regrouping of the things. So you can make uh, so you have an sum of m things and you are grouping it into group of size m1, so you would be left with m2 such groups. So that's this product. And this is 0 because m is the characteristic by definition. And m1, so m1 m2 both are greater than 1, so they have to be less than m, both of them. So that implies m1 of 1 is non-zero, m2 of 1 is also non-zero, because m is the smallest integer such that m1 is 0, being the order of 1. So m is the smallest integer such that m1 is 0. So m1 of 1 and m2 of 1 cannot be 0 because m1 and m2 are smaller than m. So we get a zero divisor. So that's a contradiction. So that's a contradiction because field cannot have zero divisors. So this is a contradiction. Contradiction as f is a field. So you cannot decompose characteristic non-trivially. So it cannot be a composite number. It has to be prime. So every finite field has characteristic prime. Uh, so that being said, we can say something about the order of a general finite field, and that's the next thing. So that's the first theorem. Order of a finite field f is of the form p to the n, where p is a prime and n is an integer greater than equal to 1. So this theorem tells us that every finite field has order of this form. The form is p to the n, where p is a prime, so they are all prime powers. So how does we prove this? So proof of this fact. So let's define a map from integers to the field by sending m, an integer, to this thing what we have already defined. So this is just addition of 1 m times. So this is not in m into 1. So because that is not defined, m is an integer, 1 is from the field. So this is m into 1 is not defined. It is just the sum of m once. So you take 1 repeatedly m times and add them. So this defines a ring homomorphism, which is easy to check. So integers form a ring, and this f being field is of course a ring. So this is a ring homomorphism, and a kernel of this. So kernel of phi is So this consists of all the m in Z such that m1 is 0. And this is going to be all multiples of Z, all all multiples of P. So all multiples of P, where P is the characteristic. That is just easy to see from the definition of characteristic. So where, and that's a prime. P is the characteristic of F. So therefore, by isomorphism theorem, you can say that Z mod Pz is isomorphic to the image of, and so Z mod Pz. So this is same as, so this quotient ring is just the same as this integers modulo P. This was our earlier notation. That's the notation we started with. So these two are same thing, and this is a field. So this is a field. So therefore, so what is the picture we have? So we have this finite field. So that's the situation. Uh, So okay, so let's write this as, so we can identify. So we can so we have an isomorphism. So we can identify this the ZP with the image, which is sitting inside F, the finite field. Identifying ZP with, because that's an isomorphic copy, with image of phi, we have this ZP. So ZP is, we can simply consider this to be inside this. Okay, let me write it here itself. So we have ZP sitting inside it. So both are fields. So both are fields. So you can, so then, so both are fields. So the bigger fields become a vector space over the subfield. So then F is a vector space over the subfield. So if you have one field containing other, then the bigger field is a vector space over the smaller field. And F is finite field, it's a finite set itself. So this is a finite dimensional vector space. So we have an well-defined quantity, which is the dimension, say n. So suppose n is the dimension of F over ZP. So whichever way you want to write. So this is, you can write it as ZP F. And then the cardinality of F is going to be P to the n. So that's simply because if you take a basis, so if so let me just write a small explanation. So if E1, E2, En is a basis, is a basis, then any x in F or alpha in F, maybe alpha in F is written uniquely as it's a basis as alpha equal to A1 E1 plus A AN EN, and all these AIs are coming from the subfield, which is ZP. So that has P elements. So you have P choices for these coefficients. So the total choice of such expression is P to the N, and every element of F is written uniquely in this way uh, because it's a basis, and that's the reason for this cardinality. So every finite field has to have order power of a prime. So it's always going to be power of a prime. So that's the first. So we now understand the order of fields. But of course, the important question that arises is that given a p and an n in a natural number and a prime, can you construct a field of order p to the n? So we would address it uh, just little later. So let's see some other properties. So by the way, I haven't explicitly mentioned, but it's always the case that whenever you have a problem, please stop me and ask. So any amount of interruption is fine. So okay. So let me just change page. So next we are going to look at the multiplicative group of non-zero elements. So that also I write it as a lemma. If F is a finite field, then the multiplicative group uh, if so I should just have a notation for this. So let's write it as just with if multiplication. So by this I mean f minus 0 with multiplication. So let's just have this notation. Rather than writing this full thing again and again, just write this. So this simply means f without the additive identity. So all non-zero elements, so to say, under multiplication. So that's a multiplicative group. And this lemma says that this multiplicative group is always cyclic. So let's prove that. Of course, for ZP we know that, but in general it is true. So let Q be the order of the field, then Q is P to the N. So P is always going to denote prime. P to the N, P is prime. So this is from the last theorem, that order of any finite field is of the form p to the n with a prime p. And this p is also the characteristic. So f plus if multiplication, sorry, the multiplicative group has order q minus 1. So we simply want to say that there is an element in f multiplication which is of order q minus 1. That will tell us that this group is cyclic. We need a generator. So we need to find an element which is whose order is equal to the order of the group. So let M be the maximal order of an element in F multiplication, in this multiplicative group. F be the maximal order of an element in F, the multiplicative group. Then, so order of any element divides order of the group. So M of course divides Q minus 1, and it is in particular M is less than Q minus 1. So we want to show that M is equal to Q minus 1. So we want to show, let me just change color. M equal to Q minus 1. So I would just need a fact about abelian groups. Uh, so I'll just state that. So a fact. So I'll just state it as a fact. So in a finite group, it has to be abelian. So in a finite abelian group, order of order of any element divides the maximal order. So just using a fact from group theory. Maximal order. So in particular, in this group, every element, order of every element, every element is going to divide M. So this we are going to use. So this we are using without proof. Now for all t, so if we use that, that's going to tell us that for all t in if multiplicative, t to the m is going to be 1. Because any element, so order of any element divides the maximal order, and maximal order is m, so t to the m has to be 1. So therefore, all the elements of F cross. So all the elements of this group are roots of this polynomial. So roots of the polynomial x to the m minus 1. So every element of F cross satisfies this equation x to the m minus 1, because for any element t to the m is equal to 1. So this follows from this fact. Now we would require another fact. A polynomial of degree n over a field has at most n roots. At most n roots. So if you use Euclid's division algorithm for polynomials in fields, so then you can easily obtain this. So just by comparing degree. So for every root, you would have a linear factor, and then if the degree is n, you cannot have more than n linear factors, because otherwise the degree won't match. And so in a field, so that is of course true in our integers and rationals. So and this can easily be proved over any field. So therefore, so the number of root has to be less than equal to n, and therefore the polynomial x to the m, so x to the m minus 1 as less than equal to m roots in f in f in f in f is a field, so it has m roots in f, and of course 0 is not a root, so all roots are in f, in the multiplicative group. And that so it has so all the elements of f satisfied this polynomial, so they are all roots, and we have at most m minus 1 root, and this so here we have q minus 1 roots, because if I think that is the notation we have, yeah, so q minus 1. So if this multiplicative group has q minus 1 elements, and therefore we have q minus 1 roots, and number of root is bounded by m, so q minus 1 is less than equal to m. So we have two things. One is m divides q minus 1, and also q minus 1 is less than equal to m. Therefore, they have to be equal. So that would imply that q minus 1 is equal to m. Just a second. Or let's write m equal to q minus 1. Yes. So what we proved is that the maximal order of an element in the multiplicative group is q minus 1, and that is what we wanted to prove. So we have an element, though we haven't constructed such an element, we know the existence of, so we just derived the existence of an element of order q minus 1. Therefore, the multiplicative group is cyclic. Okay, so one thing about notation. So just notation. So we would follow this. So we write if q for a finite field. So that's the standard notation followed in every book. So for a finite field of q elements of all right finite field of q elements. So that would be a standard notation. Okay, so a small remark here. So if the multiplicative group is cyclic, that's what we have seen. So is the additive group cyclic? So additive group is, so if you look at the additive group, then every element has order p. So if you add, so p being the characteristic, so p being the characteristic, so that is our standard notation. So p is the characteristic. So just write this characteristic of f. So every element has order p. So f plus is, or just write like this. So every element in, let me write it in this way. So every element in f plus has, so that in the additive group has order p, p the characteristic. Therefore, if p is cyclic, if q is p, so that is the field has p elements. So if the field itself has prime order prime, only then f plus is cyclic, otherwise not. But if the multiplicative group is always cyclic, that is what we proved. Okay. Yes. So now the thing is, how do we construct finite fields? So how do we construct finite fields? So here is a general way, so that we write it as a theorem. So just calling it construction of finite field. So this construction is going to be a theoretical construction. Later on, we would see how to actually construct fields. So given a base field, how to construct extensions and things like that. We would do it. Probably also we would do some algorithm to do such things. So for the time being, we'll just concentrate on the theory to know what it is, what to expect. So construction of finite field, and I write it as a theorem. So let kx be a yeah, actually we don't need monic. So we take an irreducible polynomial, so which cannot be factored into polynomials of smaller degree of degree r in fp of x. So this is a polynomial in fp of x. So fp is our zp. So I should just clarify that notation. So q is a finite field of q elements, and therefore we also write. Uh, so we would use fp to denote zp. These two are just the same thing. So this is so zp integers modulo p is a prime is a field of p elements, and we write it as fp as well. So use both notations, then that should be fine. So f of q is going to be the standard notation for finite fields with q element, and that's what we are using here. P is a prime. So, kx, let kx be an irreducible polynomial of degree r in this ring, the polynomial ring. So this is a polynomial with coefficients from fp. Define. Oh, sorry, let's change this. So we define an equivalence, we define a relation, and then of course afterwards we prove it to be equivalent. So equivalence relation. So we define a relation say tilde on if p of x by so ax and bx, so they are of course polynomials from if p of x. So ax is related to bx if and only if. That's how we are defining. If kx divides ax minus bx. So just congruence in just congruence with polynomials. Then the set of so this turns out to be an equivalence relation, and the set of equivalence class is going to form a field. That's what we want to say. We prove it. So let me make the statement. Then the of set of equivalence classes with so usual definition of addition and multiplication. So we just simply add polynomial and then read it modulo this kx with usual addition and multiplication forms a field of p to the r elements. Yes. So let's just consider this statement once more. So if you have a polynomial kx, an irreducible polynomial in Fp, which is of degree r, then this gives a construction for a field of elements p to the r. So a field of order p to the r. So we would later see how to construct such irreducible polynomials. So now this theorem simply assumes assumes the existence of such an irreducible polynomial and then construct it. Okay. So I'm just so I'll leave the proof. So it is very easy. So it's just modular arithmetic, and just exactly whatever you do for integer is valid there, including Euclidean algorithm. So the way of finding inverse is also exactly the same. So other things are of course completely trivial. The only slightly non-trivial thing is to check uh, that non-zero polynomials have inverses, and that's easy because the validity of the Euclidean division algorithm. So then it's exactly same as in the case of integers. Okay. So the next thing we should aim is to prove that there exists irreducible polynomials. So if you have irreducible, so consider an FP, and if you have an irreducible polynomial of degree r with coefficients from FP, then you can construct this field with p to the r elements. So we should also be able to prove that there exists such irreducible polynomial. If you do not have an irreducible polynomial, then you cannot construct such a field. So just remember that we are trying to answer the question whether there is a field. So let me reframe. So given a prime and given a natural number, so given a prime p and given a natural number n, does there exist a field of order p to the n? So to do that, using this theorem, we should be able to find an irreducible polynomial of any degree over a given fp. So as soon as I find a polynomial, irreducible polynomial over fp of a given degree, then we can construct a field of p to the that many p, so p to the r elements. So finding irreducible polynomial is important. At least we would like to prove existence of such irreducible polynomials. So that's the thing what we want to do now. So what is our aim is to do this. Let me just write what I just said, the gist of it. So we aim to prove the existence of irreducible polynomial. So for every prime p and every integer n greater than equal to 1, natural numbers, there is an irreducible polynomial. There is an irreducible polynomial of polynomial in say ZFP P of x. So polynomial with coefficients from Fp, uh, which is irreducible and of degree n. Yes. So that whatever natural number you start with. So this is the m. This is our m. So we need several lemmas to establish this. So let's start with the lemma. So most of the lemmas are quite interesting on its own. Let A be a finite field, be a finite field with Q elements. Then for any element A of F, A to the Q, I would just write it there. So A to the Q, okay, sorry about this, if it looks same. So A to the Q is always equal to A. So so this is a finite field of Q elements. Then for any element A of the field, A to the A raised to the Q is equal to A. So prove that. So for a zero element, of course, it is trivial. Both sides are zero. For A equal to 0, it is trivial. If A is not 0, that is, if A belong to the multiplicative group, then this A. So should not look like Q. So once. So A is an element of the multiplicative group, and this multiplicative group has order Q minus 1. So order of an element divides the order of the group. So therefore, A to the Q minus 1. So whatever be its order is always a divisor of Q minus 1. So if you raise to the power Q minus 1, you're going to get 1. And that implies, so if you just multiply by A on both sides, then A to the Q is A. So that's a very simple lemma. We need a definition from general field theory, which is about splitting field of a polynomial. Very natural thing to uh, define. So this is a splitting field. So let fx be a polynomial, uh, be a okay. So just write in notation. So fx be a polynomial in kx. K is a field. Let's write capital K. K is where K is a field. So then the smallest smallest field, so smallest in the sense of inclusion. So inclusion is the ordering there. So that's of course a partial ordering. So then the smallest field, uh, if say if containing k in which if x splits completely or I can just write where if factorizes into linear factors factorizes completely. So all the factors become linear. So factorizes completely. Let's write factorizes completely into linear factor. Factorizes completely into linear factors. So what I mean is if x, okay, let me just finish the definition. Linear factors is called the splitting field. So what I mean is you have a polynomial fx with coefficients from kx. So with coefficients from kx, and so if you have a field f containing k such that there exists some alpha 1, alpha 2, alpha n elements in f such that fx is x minus alpha 1 and x minus alpha n. So we can consider this to be monic. So the first coefficient is considered to be 1. Otherwise, you can just take this out. Or you can even write with a constant. That doesn't matter much. So what you want is to write f as a product of linear factors. So you can completely factorize f. If that happens, then you say that f please splits completely in f. So f splits completely in f, and if it doesn't split completely in any smaller field, then f is the splitting field. So if f is the smallest field with this, in which this happens, this complete linear factorization happens, then it's called the splitting field. So splitting fields exist and it is unique. So that is a fact we have to assume from the field theory. So that comes from general field theory. So we would have to assume that. Splitting fields exist, and so given a polynomial, they are unique up to isomorphism. So if there are two splitting fields of the same polynomial, then they have to be isomorphic as fields. So we can think of them to be the same field up to isomorphism. So in fact, intuitively, it's not such a difficult thing to imagine. No, I'm not saying that it's completely trivial to prove, but it's not difficult to imagine because if you have a polynomial fx with roots alpha 1, alpha 2, alpha n, suppose these are all its roots in some very large field that which contains all these roots. So suppose you have a field which very large field which has all these roots, and this is on kx with roots alpha. In fact, if you think of fields, if you think of say q x, for example. So if you think of polynomial in qx, so if you think of polynomial in qx, so polynomials with rational coefficients, then of course they you can always solve them in complex numbers. So all these roots, so you can completely factorize and get all the roots in complex numbers. So there is some field. So it's not just difficult to take that there is some field which contains all the roots. So in this case, we know that so every polynomial will completely factorize into linear factors over complex numbers, and so from that understanding, you can imagine that this generalizes to any field. So we are not proving it. So if you have all the roots, then how do you get the splitting field? So to get the splitting field, you can simply attach all these roots to the ground field, to the field on which this polynomial belongs. Uh, so, uh, so, so this is essentially the smallest field which contains k and alpha 1, alpha 2, alpha n. So this is the smallest field containing. So if you take the smallest field containing k and all the roots, that would definitely be the splitting field. You cannot split the polynomial in any smaller field, and this is enough. And here it splits. So splitting field would be the smallest field containing k and alpha 1, alpha 2, alpha n. So that is sort of supports the idea of this finite field, existence of finite field, and they are also unique up to field isomorphism. So this we are going to assume. So this is just for motivation. So it is not, it is nowhere near a proof. Okay, so I just have a little time left, but we have actually done. Uh, yeah. So with this assumption about existence and uniqueness of finite field, we have a very nice lemma for finite field. So F be a field with Q element as always for us. Q elements. then the polynomial zx to the q minus x. So that's just a polynomial in if yeah. So this is a polynomial in sorry, I write if p of x. So this 1 minus 1 is coming from f p. So polynomial in if p of x, this splits in fx, splits in f, or you can write fx, yes, as x to the q minus x is product of all alpha belonging to fq x minus alpha. So this is a particular polynomial over fp, and if we are filled with q elements, yeah. So with this is always the assumption that p is the characteristic. Mm, okay, let me just write it here. So p is the characteristic of f, and q is a power of p, say p to the n. So that would always be the notation. So p would, unless otherwise mentioned, p is a prime, which would be denoting the characteristic of the field, and order of the field is a power of p. So what we are saying that if we have a field of element q, then this polynomial x to the q minus x splits completely in f. So how do we prove this? So x to the q minus x okay. So and we also say that this is the smallest field. In other words, this is the splitting field. And so add that if is the, so we are using the for splitting field because it is unique up to isomorphism. So up to that identification we used it is unique, so use the. So the splitting field of x to the q minus x. So this polynomial splits in f, and by splitting field we mean that it cannot split in any smaller field. So proof actually follows from the last lemma. Yeah. So what did we write? Yeah. So we have this lemma that every element of f satisfies this equation that x to the q equal to x, namely this a to the q equal to a for every a in f. So every element of f satisfies this polynomial. So by the last lemma, every element of f satisfy x to the q minus x. That would mean f contains q roots, because there are q elements of this polynomial x to the q minus x, but it's a polynomial in our for a field, so at the number of roots are q, so x to the q minus x, uh, but x to the q minus x has at most q roots in f. So that amounts to saying that f contains all the roots. So f contains all the roots. In fact, even more, f is the set of all the roots. So because every element of f satisfies this, so every element is a root, and these are all the roots because it cannot have more than q roots. It's a q degree polynomial. It cannot have more than q roots, and if every element of f is a root, so f is essentially the set of all its roots. So f contains all the roots, and obviously it is the splitting field, meaning you cannot split the polynomial in any smaller field, any proper subfield of f. Field. Yes. So, okay, time is up, so I would stop with that. Any question is welcome, and of course, so you can just unmute and ask. And of course, we have the tutorial on Sunday to discuss this, and I would send some problems by tomorrow morning. So I'll send some problems by email, so which you can try. That will give you examples as well for the theory that we are doing. Yes. Yeah. So Dr. Gurushami, I would just stop and just wait for questions.
Okay, sir.
Okay, sir.
So I would also like to add that I would be sending the notes, of course, but I just need to correct some handwriting because some of the handwriting is bad. So I just correct a little bit and send.